Okay, year 13, in the first section of the chapter then was basically how do we create the X-rays. What we really need to know now is actually how do we create the X-ray images. So how do X-rays shining through a person or other objects, because of course you can get imaging of other things, how does it actually form an image? What is the process that's going on inside? So starting to dive into the deeper aspects rather than the thing itself, rather than the general picture. But if we start with that, so we've got our X-rays, what is going on in the leg, so that when we actually come through to form a nice clear image, this aspect we'll look at later, we form a nice collection of X-rays to produce us an image, which we then nowadays put into a computer and do the analysis with that. Principle's not much difference from shining it onto a photographic plate instead, like in the original picture. So let's go into this. We've had a look at the basic processes, as I say, of what's forming the rays, and we can fine tune all this. However, how do we actually form the image? Well, we'll go back to basics, because in the end it's actually just based around the same systems. Okay, so if you are shining waves of any variety, in this case X-rays, but of any variety, if you're shining it into a substance, you get 4 basic effects. Okay, mainly 3, but it varies with the type of wave. So if this, for example, was your bathroom mirror, then most of the light is reflected off, which is what we use the mirror for. However, it's only reflected off really well at visible wavelengths. We will still get some rays going through the glass and through the mirroring. Some of it gets absorbed, so some of that energy actually disappears into the material, making the material warmer, and some is scattered by the actual atoms within it. So slightly different process. Now, visible light with a mirror, most of it's reflected, very little of these. However, if you try looking at UV wavelengths and even infrared wavelengths, you get much less reflection. There's a lot more going on here. Okay, so much more proportion of these things. And the principles happen with all waves going through all substances, so that's what we're going to have a look at. So with X-rays, most of it will pass through. There's very little reflection, unless you happen to have metal plating or something, because that's quite good. But what we need to do is we need to basically think about the processes a bit more, because unlike visible light and other wavelengths, you can't really do much with the beam. It's very difficult because it doesn't really refract as it transmits through. It doesn't really make it easy to focus. So if we want a nice clear image, we need to use and know the processes and use some other techniques to make it happen. Okay, so the first thing is, it's all over the place. When we have our X-ray tube, if I just go back to my little sketch, X-rays basically shine out in all directions. So that's one of our factors straight away, because as the rays disperse, the energy actually being deposited on our detector is really small. So how does that work? Well, it's all about the intensity. So if you just go back to way back when we did light, your very first starting place is that equation that most people don't realise is an I, because it just looks like a 1. Is basically the idea of power over area. Okay, so the power deposited, and I'm going to just put it in another way, so the energy at a point, energy deposited. If you're thinking about forming your image, it's deposited at detector per second. Okay, so it's literally measured in watts, or if you prefer joules per second. And that's cross-sectional area, so however much it's spread out. And that, using the SI units of meters squared, then gives us our standard unit for intensity, which will be watts per meter squared. Okay, so that's our our basic idea. and the further you are away from your X-ray tube, the more the power is spread out over a bigger area, so it gets less and less intense, which in terms of image means your image is just darker. Okay, so you want to get as much intensity through that you can, because that will give you a bigger, more contrasting image. That goes back to our idea of voltage. Looking a little bit further, let's dive in a bit more. What that means is that we can break it up a bit more and think of it in terms of the butter gun. It's that surrounding sphere, that bubble as it spreads outwards. So if you were to have a single point source of a certain power, then of course it is radiating outwards three-dimensionally, not just two-dimensionally like on your page. So it's spreading outwards as a bubble, so it's thinning out over that surface area as your bubble swells up. Now, to understand the processes, in the original days we just talked about intensity, but we can make it a bit more simple, I think, if we think about it in terms of quantum processes. So at a quantum level, it is of course photons rather than waves spreading outwards. So we can do the equivalent and think about the equivalent model as large number of photons, energy of each photon. Okay, so that gives us our total energy. I'm just going to put per time over there, so that gives us our whole idea for large n, just like with the large number of particles in gases. So for n photons, and of course it's spread out over that 4 pi r squared. So we can play around with the mathematics, which is the main point of just doing this now. Questions can be looking at that, but in terms of as principles, that is, but in terms of our X-rays, basically have a think, and I'll put it in here. Number of photons per second is basically let's say it's due to tube current. As the phrase is. Okay, so you won't see that in questions, but again, use the logic. Number of electrons flying across the gap in your X-ray tube, okay, being accelerated by your high voltage. Number of electrons per second will give you more photons per second. Generally, one electron will release 1 photon. Okay, although at these levels of energy you could have a bit more. So what we tend to do is we will often need to get around this effect, because there's 2 or 3 effects from this. The second point is that this would be one point on your target, but your target is quite big, and so they're scattering off in all directions from actually a whole line of places, so it's not quite this clear. Also the fact that you have these crossing beams of photons from all these different sources means that your rays are going to cross over, your photons are going to go into different places, and so you won't get a clear picture. Just in the same way that if I put my hand here, it's really quite a bad shadow, because the light is coming in from different angles. If I turn a light bulb on, then I'll get quite a nice clear shadow, because it's a point source, or much more of a point source than the sunlight outside. So, as I said, we'll come back to it later, but that's the whole idea of what we have here. So often the first stage is to try and use a collimator, so that it produces columns of light, and only the light that's coming straight through to line up with these holes will actually form the image. So you get a clearer image, right? As I say, we'll look at that later in another part of the topic. Okay, so if we use the collimator at the beginning, so put a bit of a collimator on the tube, then we don't really get this effect, because it's not really spreading out. You've taken away all the rays that aren't there. However, we then go into the idea of, okay, what's going on? It's a bit clearer to see what's going on as we go through the body. So you know, that's what we need to actually form our fairly nice clear picture, but it does mean the intensity doesn't fade out. It's not spreading out like our butter from our gum. So if we think about what's going on, well, yeah, we have absorption happening in patient, which X-rays is quite scary, so it has a limit, which is why you have a maximum number of particles, maximum number of X-rays per year, particularly on more sensitive bits of your body, because you're adding more and more energy. So, should we ban them? Well, the whole point is X-rays work on that principle. The fact that some materials, like bones, are much better at absorbing that energy, absorbing those photons, means that we have a much better shadow caused by them, and you get your contrast between your different materials. So if we shine this beam through the person, when we're getting to the person level, we can start to think about what's going on in terms of something we have seen before, and that is the idea that we did for radioactive decay, where we basically have the idea of half thickness. So the thicker a material, the less intensity gets through, less intensity is transmitted through. So here's our original source of intensity, let's say just as you're going into the body, and the thicker the object that it's going through, the more of the photons are absorbed. As the more absorbent the material, the lower intensity out. But of course it depends on mu, and that attention coefficient is what we've discussed before, radioactivity, but here it's the idea of bones. You know, that has a different attention coefficient to attenuation coefficient to skin, muscle, connective tissue, etc. Okay, air in the lungs and so on. So really common basis of the question, okay, because it's about this idea of how we form the image. So just make sure you're happy with that. We'll have a little play with some maths and have a quick go now. So I should point out this value does change. As noted down here, certain energies of X-rays are better at being absorbed. So we can fine tune things. So we do need a bit of a more detail if you want to go full maths on this. But we're going to go through the basic ideas, which is what we're working at A-level. So here we go. Collimated beam goes through 2 centimeters of material. The final intensity is 0.1 of the original. So 10%, 1 out of 10, 10 out of 100, however you want to think about it. So let's go for the, as usual, the more useful way of doing these maths, which is to think about ratios. So that's going to be e to the minus mu x, if we just rearrange that equation. But you're getting very little out. So 0.1 is this fraction here. So if you put that in, you can ignore that now. It's about finding the value for mu. We know what x is. Let's go with the whole idea and just rearrange. So natural log, to get rid of that, natural log of 0.1 equals minus mu x equals minus mu, and I'm going to do it as a fraction to make it clearer, 2 centimeters, not meters, so 2 out of 100. And if you put that in, then what you'll get is your answer, which will be 115 per meter. Okay, clue being in meters. If you did it in centimeters, then your answer would obviously be different. It'd be 1.15 per centimeter, for example. But yeah, stick with the standard units, make it a little bit easier. Half thickness, well, we've done some practice on that, and again the same idea. So I over I naught equals half. So log of 0.5, use that rather than fractions, equals minus mu x half. And if you put that in, then what you'll end up with, you can do the maths, 0.693 divided by that value there. In fact, we'll do it just to make it clear. So x and a half for this material is going to equal minus log of 0.5 divided by mu So minus, which should be 0.693 over 115. So for this material that we have here, you'll find that half thickness is around about a much more user-friendly, rather than this value, much more user-friendly idea, which is about 6 millimeters. Okay, so again, just check your answer to that won't be directly this, it'll be 0.006 meters, therefore more user-friendly. So 6 millimeters of this material will halve the amount of photons getting through. It will halve the intensity. Okay, so bit of revision again, all the same kind of stuff. It's stuff you've seen before, but fairly common use of questions. But how does it get absorbed? That's where the difficulty comes in, the idea. So what we're going to look at now is the idea of how do we actually get this attenuation, as the phrase is. How do we get this decay in the numbers? And X-rays, it is a little bit complicated. We have some basic principles, but because of the energy, we have some other principles going on. Okay, so first off, we'll just go with the basic idea that happens at a lot of energy levels. It's not just X-rays. So anything with a low energy interaction, so low frequencies, not no velocities, of course, because they're photons of light traveling at the speed of light. What you find is it's not enough energy to change the atom itself. Okay, so what we basically got is a very simple effect where, and we'll get this basic start for all of them, E equals HF, and I'll just put on low just to drive it home there. Because we got that low frequency, what you'll find is it's just literally deflected, badly drawn there. So it comes out with the same energy as it goes in. Okay, so that's basic effect of reflection. If you think about it, photons go in, photons bounce back out again. And if you use certain materials, you get a nice regular effect, so it's easy to see. So that's actually happening for all photons, okay, whatever this idea is. But X-ray photons, some of the energy as part of that scattering graph is caused by this. So energy absorption effects are caused by this, but very little. More of them are the following three, the following two in particular. Okay, so the first one is, well, if you've got photons coming in with enough energy, UV for example, then metal will easily release electrons as long as you're above the work function. Well, your bones are calcium based, calcium is a metal, so the fact that it's buried and the fact that we lose energy on the way and so on and so forth means that we need higher energy in principle, but X-rays are enough to actually ionize calcium. Now if you think about it, that's a slightly worrying effect in the body as well, so again back to this idea of limiting it. But yeah, so we have our whole, energy in is HF. Okay, and that, I'll put it that way, turns into the idea of depositing some with your work function plus the kinetic energy of ionized, electrons. So let's just be precise with these. So here is our photon, okay, because I know that some people get confused with it. We're looking at energy in, so you know this same effect will happen if we were to fire electrons in and things in other cases. Okay, so just the general principle is energy in, energy out. Certain amount of energy is wasted, shall we say, is used for something. So that's your work function, and that is of course the minimum energy to release electrons, an electron, or each electron, and this is of course the electron that's emitted. So I'm going to call it its more generic name, which is, just to define it, a photoelectron. Emitted. Okay, So that's exactly the same process before, it's just not nice, shiny, clean metal, it's your bones instead. So what we're thinking of in terms of what's going on inside is that basically, because of the high energy here, this is so much more excessive than this. Okay, so this is way higher in excess of the value of this. So effectively, for this value here, HF is much bigger than phi. So HF is approximately equal to the kinetic energy. Let's put a so. There we go. And that's our principle behind it. So it's quite easy to work out what's going on. It's quite easy to see how much electrons come in. So again, each photon coming in is going to actually cause one of these, whichever one it strikes, to jump out with your kinetic energy. Okay, and how much kinetic energy depends, of course, on the work function. So how tightly bound it is, how much work needs to be done to remove it. Okay, so that minimum energy required or the minimum work done, hence work function, if you've ever wondered. Okay, so these are high-speed electrons. These are actually causing damage in this effect. You are knocking electrons out of your substance, okay, out of your bones, out of your other tissue as well, but bones is where they're actually coming from. Because metals are easier giving up their electrons. So there is an effect going on. We do need to kind of worry about this. We do need to think about this. So again, this is one of the causes of, but also uses of, X-rays to image. Okay, so what have we got going on? Yeah, effectively, as I say, it's very small. Other than that, it's really nice, simply done. Okay, it's stuff we've studied before. Now, the main technique, and this is where it gets a bit more strange, you may think. There's lots of discussion about this if you look on medical imaging websites or medical physics imaging websites, so discussion on what the effects are and so on. So this differs, it's similar but differs from photoelectric effect. Okay, this one comes in, okay, and is absorbed. Okay, so all that energy is released because the photon no longer exists. This one isn't. This is slightly different. So what we're getting on here is, and it's a general effect, I should say again, it's not a medical effect, it's a general effect for anything that is a very high energy. So again, we have our X-ray coming in. Dun, 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 dun. Okay, so I'll label this up. It does not happen at lower frequencies. Okay, so it does not happen at lower energies. You need quite a lot of energy. So what effectively happens here is what we could describe as an inelastic collision. Okay, so scattering up here, this idea of reflection, is basically an elastic collision. We don't lose any energy. The energy of the photon in, energy of the photon out is the same. This isn't. This is very different. And so what you're getting in this effect is the same kind of thing as up here, but energy is used to have a similar effect to the photoelectric effect. I think I'm going to go down this time because there's a bit more room. So here we have our electron emitted. Okay, or electron is lost by the atom. Okay, fluorine, calcium, whatever it may be, so some metallic compound. Some metallic atom. So that happens, but the photon carries on. Not quite carries on. It has lost energy. Now this effect, this scattering effect, is really common with particles. Electrons come in, collide, knock something flying, but carry on with less energy. They go slower. Now these are photons. They travel at the speed of light. They can't go slower. So what we have to manifest itself as less energy is that these still have a photon there. So I'm going to say photon continues, But how do we get less energy? Well, we've got to go for this. So if energy is down, then frequency is down. Okay, so we actually get a longer wavelength photon being emitted compared to the ones that went in. Okay, so this can cause glowing and things like that, makes things appear to glow and so on. But yeah, Compton scattering is an inelastic collision. Okay, and I think I've put it in there somewhere. Dum, dum, dum. The whole idea is photons do have momentum. Okay, difficult concept because they don't have mass, but they have this idea of apparent mass because they do have this idea of energy and momentum. You can't have energy without momentum as well, movement energy. So it's the fuller version of Einstein's law equation that we haven't done. But yeah, they effectively do have momentum, and you need to conserve that momentum. So it's a bit like a shock wave. That energy released due to the shock wave means that there's enough for the electron to be released, but because of that, photon also has to go off in the opposite direction, basically, deflected away from each other, as it says there. So why? Because they have to conserve that momentum. But because that's taken some of the energy, that's got less energy. Okay? Equals inelastic collision. So if you had to describe it, the simple way to talk about Compton scattering is that you have an inelastic collision between an X-ray and an atom, which releases an electron, and the photon has less energy afterwards. It's a lot deeper than that, but that's enough to kind of get around the idea of it. Okay, so that's working at these kind of levels. It's only there where you're starting to see this noticeable effect, this idea of a recoil. So have a go with that. I've really had a clear think about that. That's as clear as I can make it. So hopefully that's good enough to kind of understand. Now there is a fourth process as well, which we have looked at before, and this is really high energy. So if you're looking at really high energy, then what you can get is when your photon comes in, again, so high, I mean the last one was high, but this is even higher frequencies generally, then what you end up with is those basically act as targets. Now to be fair, this would deflect an electron, so I'm going to carry this on, and basically when it's more likely to hit the nucleus, by far more common, that's not going to go anywhere. That energy is released, not enough to release a neutron or a proton from the nucleus. So what you end up with is a pair of particles being created, and the easiest ones, the least massive ones, are of course electron plus and electron minus. So an electron and a positron. Okay, so in that effect it's the same as before. Again, they go off to conserve momentum, so they're flying forwards, both flying forwards because of that momentum of the photon, this momentum idea of light, but they will disappear off away from each other in opposite directions. How does that work? Well, of course, it's energy in, HF, equals E equals mc squared. Okay, so it's all about still the principles of thermodynamics. Energy is conserved. So energy in equals energy out. But don't forget you're creating a pair. So it's 2 mc squared. So those are the four processes. As I say, the processes don't just happen in X-ray imaging, they happen all over. So, you know, normal everyday process of scattering of photons, so the photons come back out again. Effectively the same photons, well, it is the same photons coming back out. Photoelectric effect, where you've got a bit more energy and it's enough more than the work function to release these. This will of course work at UV frequencies upwards because they are ionizing, so we are creating your ionization effect here. Okay, so photoelectric effect is the prime evidence for ionizing effect of radiation. So X-rays will do this, gamma rays will do this, and of course UV will do this, okay? But X-rays will do it in the body with the metal of bones. Compton scattering, higher energy, so if you're doing hard X-rays, you're looking at the bones, you're going to get some effects from that, and again, that's causing damage to the atoms itself, or the material which is made of the atoms as you ionize them, and so, yeah, again, destructive to some extent. That's again why we limit the amount of stuff going on. Okay, amount of X-rays you're taking. Pair production, less so. It's giving it heating effects. There is energy bound to be lost in this process. So in the ideal case, this is it. But yeah, you'll probably need more energy than that. So minimum photons. So let's have a look at a couple of questions, as it says there. Minimum photon energy required to create that pair. Well, let's go off with the idea. So go into the front of your data book, mass of electron. Maybe you know it by now already because you've been kind of seeing it quite often. 9.11 times 10 to the minus 31 kilograms. Okay, so not very much. So 2 times mass of electron is going to be, of course, twice that. So that's going to be 18.22 times 10 to the minus 31. Okay, and again, I'm going to keep putting this into my habit so I can follow where my data is so I don't get lost while I'm doing the question. So useful to put units as you're going through. Okay, so our energy in is going to equal your mc squared. I'm not going to worry about that bit at the moment. So mc squared, which is going to be, as I say, 18.22 times 10 to the minus 31 times by 3 times 10 to the 8. And that's squared, and just to make it clear, I'm going to put that in brackets so you can remember and see more easily that it's squared. Okay, and that will give us 1.64 by my calculations, 10 to the minus 13 joules. Okay, so that's how much energy you need from your photon. Okay, if you do a little bit of playing around with that, 1.6 times, okay, 1.9 times 10 to the minus 19, start that again, 1.6 times 10 to the minus 19 is the charge of an electron, so this is basically a roundabout, a useful kind of thing to remember, about 1 mega electron volts worth, so a more convenient unit for visualizing. So to make 2 electrons, about a mega electron volt you need. Obviously, from that you could do the next step and work out the frequency, okay, if you needed to, or the wavelength, more common. Okay, so that's the kind of questioning that goes on in these papers. Again, just the wave equation. So, second bit of the question, what will happen if the photon energy was higher? So, any excess energy, sorry, extra, not necessarily excess, but any extra energy turns into kinetic energy. Of what? Again, ignoring the fact that energy may be lost to the nucleus, well, it will be, sorry, but of the electron pair. Okay, i.e. the two of them together. Okay, let's work it backwards. A little bit of a twist on things. Again, if you did have a photon of slightly smaller amount of energy, i.e. we don't have as much going on, so this process here is not pair production. Okay, it could be the Compton effect, but let's assume that it's just going to be photoelectric effect from the phrase photoelectron. Okay, so for that one, we'll just work on the idea of that. So we will need a value, so I'm going to say we are firing it into copper. So the metal is copper. It could be anything. And I'm using copper because it doesn't tend to come up in the questions. So phi work function for this is around about, what have I got written down? There we go, 7.36 times 10 to the minus 19 joules. Again, of the order of the charge of an electron, so it gives you an idea, kind of things to look for, how kind of big, does it sound right, etc. So, kinetic energy, well, it's going to be HF minus phi. I've just rearranged it in one go straight away. So what we end up with is, well, again, just be careful you don't jump in with both feet. So that is the energy of the photon. So 1.6 times 10 to the minus 14 subtracts that 7.36 times 10 to the minus 19, and you're going to end up with something fairly about that scale. And I get basically 1.6 times 10 to the minus 14 if you do it to two significant figures. Exclamation mark. Why? Because the work function is tiny compared to X-ray photons. Okay, so again, don't be surprised. Perhaps you could do this and just say negligible, or you could just put it in and just ignore it, or of course just put it in a calculator, but don't be surprised if it's basically, it's the photon energy. Okay, that's going to be the energy of your electron come out. So velocity of it comes from that. How do we get that? Well, we can work it backwards, but the fairly obvious thing for us is, sorry, into other areas I was going to say, is of course half mv squared, and in this case you only have the one photoelectron, so v squared, again I always do it like this, 2e over m, because people keep forgetting to do the square root. So if you keep it v squared, okay, then you could do it as, lay it out nice and simply. Okay. Sorry, times 10 to the minus 13. Then what we've got there is going to be 911, of course it is, 9.11 times 10 to the minus 31. And done. And so I then jump, I get my answer in my calculator, I know that it's V, I don't need to write that necessarily that value down. It's worth in the exams though. 1.87 times 10 to the 8 meters per second. Okay, so pretty damn fast. Why? Because it's X-rays. It's pretty damn high energy photons. Okay, so that's the kind of the big link about it. If you wanted to, you could do a little bit more, so that you end up with different effects. Interesting. I've just spotted notes in my old problem with my own notes, ignore that bit. So yeah, you know, we can work out the velocities from that. They're pretty damn high. If you needed to, or more likely, then they'll probably give you the frequency or the wavelength of the photons. You've just got one more step to do to work out, etc, etc. So again, maybe hc over lambda might be a more convenient unit for the thing you're doing. Okay, so there's quite a lot of hard stuff in that, but the principles are things we've seen before, apart from this weird wonderful Compton scattering effect. I've not seen calculations around this other than the principle that basically this is photoelectric effect. So they would describe it or state the Compton effect and maybe tell you what the frequency of the other photon is. So what is the energy of the electron? Just to round this all up, I'm going to call this energy 1, over here energy 2. Energy of this equals simply energy 1 minus the smaller energy 2. Okay, and that will be an electron, how much energy is left over to go into basically the photoelectric effect. So that would be a really, really hard question. It's not in terms of concept, it's way beyond any that I tend to see. But again, energy in equals 2 energies out, so just add up to, these add up to that. And the ones that go for the electron, well, again, that's your energy going into that. Okay, so maybe think your way through that, but actually most of the time it'll be about a question about photoelectric effect more than anything, or perhaps describing the idea of Compton scattering rather than a calculation. Okay, but if you look at those, they're calculations we've done before. Right guys, that was a long section, that first section, but it wouldn't be one lesson obviously. A lot going on there. Practice it through. There's some questions in the back. They're just the standard equations that we've used previously, just through the context of imaging with X-rays.